Hello, everyone. Welcome to the fifth live section of this course, which is Quantum Transport. I am Gitanjali. I'm a PhD scholar from IIT Delhi, and I am the TA for this course. So we are now in the fifth week of this course, Quantum Transport. In the last week, if you recall, we went through the concept, which is basically what is the quantization condition in K space as well as the real space, and we saw what is the effect of increasing the magnetic field on Landau labels, and how the longitudinal resistivity as well as Hall resistivity appears it varies as a function of magnetic field. We in detail study the graph qualitatively, and we study what will happen at different region of resistivity as a function of the magnetic field. We saw plateaus where we see the quantum Hall effect where the A state can propagate, as well as a region where the resistivity suddenly saw oscillation because of the increase in the bulk resistivity. And also, we also saw what is the filling factor and how the filling factor will change as a function of the magnetic field, as well as we saw what is Subnikov oscillation, why this appears whenever appears in the quantum Hall effect in a 2D electron gas material. So in week 5, we will see some of the concept related to what is the behavior of quantum transport in a diffusive regime. So if we recall, we went through some of the most important concept, which is weak localization, weak anti-localization, as well as AB effect, AS effect, and some of the experimental validation of this AB effect. So we will briefly, in the first part, we'll briefly go through the concept of what is weak localization, what is weak anti-localization, and what is AB effect. Also, we'll see some of the parameters such as phase breaking length, what is critical field, how this will affect the weak localization as well as the weak anti-localization. So we'll see in brief of this concept, then we'll start solving the problems related to week 5 as well as the problems that we haven't solved in the last live session. So let us start. By weak localization, we mean there is a reduction in the conductivity as well as there is an increase in resistivity of the 2D electron gas material whenever there is an coherent backscattering inside the material. So this means there is a constructive interference that is happening in the 2D material because of the two clockwise and the counter propagating waves. They interfere constructively, and because of this, we see there is an increase in resistivity because of the weak localization. So to start with, if you recall, in a diffusive transport regime, there will be scattering because it will occur when the Fermi wave vector as well as the elastic scattering length, these are less than the device length as well as the inelastic scattering. So because of this, in ballistic there won't be any scattering, but in diffusive there will be scattering, and there is no predefined path of the scattering in diffusive transport. In between point A and C, electron can travel or electron can get scattered in many ways. So it can take this way or it can take this way. So it can take any random path. So for this, for the electron or for the charged particle to go from A to C. So let us see what is the probability of finding the electron here when the electron starts the journey from here. And if we recall the quantum mechanics, the probability, the particles, all the particles, they are represented by the wave function psi of x or psi of xt. And the probability that we will find an electron or a particle in a given point, let's say x. So this is given by the square of this wave function. So the square of the wave function, this will at the point x or at the point c will give the what is the probability that the particle we will find the particle at the point c when it starts from point a. And if you see there in for point C, there are multiple paths. Let's say this is the psi1, the wave function for this path you can express by psi1, or for psi2 for the second path it is psi2, or like depending on the path you have multiple wave function. And the probability at the finding the particle at the point C, it is nothing but square of what is the wave function of the particle at point C, square of the wave function at the point C. And because of multiple path, you can write the wave function as linear combination of all this path, psi of psi I xi square for I from 1 to any given finite number. And for this, for each path, you can express the wave function in terms of amplitude, the real part, and there is a fixed factor of exponential I phi. This, I think you all know how you can write the wave function of a particle. So when you take the square of this linear combination of all these possible paths, one thing you will get is summation of ti square plus for all I equal to, let's say, j. And there will be a cross term where I is not equal to j. So for this ti, tj, or you can write tj star, or if it is real, then these complex conjugates are equal. Cos phi I minus phi z. But we can neglect this term because there are multiple scattering which is happening from point A to C. So the the phase, there is no correlation between the phase. So this phase, all this phase will cancel with each other. So what you have is the probability that the particle will go to a point is summation of Tj square, or the square of the amplitude of the wave function for all the possible path from A to C. But for weak localization, if you recall the definition, it is because of the scattering between two counter propagating waves. So because of this, instead of A to C, we are more interested in finding the probability, that what is the probability that the particle will return to this point A. After traveling through some path, it will return to point A. So this is what we call. So let us see what is the probability first, then we'll relate it to the weak localization. So for this, the probability that the particle will, it will come back or return to the point A. So there are two paths. One is the clockwise path, and another one is it can go this way also, anti-clockwise path. So according to this definition, so you can write the probability that the particle will return to A. Let's say for this path, this is Ti plus for clockwise, and for anti-clockwise, the wave function, the amplitude of the wave function is Ti minus. So this will be T I plus Ti minus square, or Ti plus square, Ti minus square plus 2Ti plus cos of phi I plus minus phi I minus. And these two paths, one is the clockwise path and one is the anti-clockwise path. These are time reverse path. By time reverse means we are moving backward in time. So these are the time reverse path. So that means the amplitude, the probability, these two are equal, and the phase that is accumulated when the particle goes through this path or when it goes through this path. So because these two paths are equal, but just it is reverse in time. So that is why the phase, the phi I plus, it should be also equal to phi I minus. So that is why this term will be 0. So we have Ti plus is equal to Ei minus, and the phase term vanishes. So that means the probability that the particle will return to point A. This is given by 4 Ti square. So this is for one possible path, right? Let's say there is a path which is area which is greater than the path we are considering before. For that path, the wave function will be different, and according to that, the probability will be same. So the total probability of return, you can write it as, this will be summation of all probability of all the time reverse path, which is 4 times of summation of Ti square. You can see it here, the probability that the particle will return is non-zero. So that means there is a substantial probability that it will return to that initial state. So this is where the weak localization concept appeared. So in such case, what will happen? These two time reverse path, one is the clockwise, one is the anti-clockwise. It doesn't matter whether it is circular or not. Only we are more interested in the time reverse part. What is the interaction between the time reverse part? Whether they are they are in mm, they are interacting constructively or they are interacting destructively. So this is all we want, and because there is a non-zero probability of return, that means if these two path. So there is a condition that they will interfere constructively, and so because of this, what will happen? Because the electron is getting backscattered, so the conductivity of the channel where the particle is moving, this will decrease because of this non-zero probability, and also conductivity decrease means resistivity will eventually increase and they will form standing wave. So that means in such case, electron, they will undergo localization, which is what we call the weak localization effect in the presence of coherent backscattering. And whenever it appears in the material, so we need to correct the conductivity of the channel by adding this, by adding the conductivity due to the decrease in conductivity due to the weak localization effect. So this is about what is the how this weak localization effect appears in a material. So what will happen now? So let us see what will happen when we put the material in the presence of a magnetic field. So whether this weak localization will survive or whether there will be an change in the conductivity or not. So classically, if we want to guess what will happen, So classically, we are more concentrated in what is the field, right? So in classical picture, this B field, it will exert a Lorentz force, and because of the Lorentz force, this particle they will appear in a circular orbit, which we have seen. These are Landau labels, and the time reverse path they will they won't coincide with each other. So then classically we can guess that there won't be any constructive interference, and it's possible that the conductivity will be restored in the presence of this magnetic field. In quantum picture, so uh, this B field they will change the momentum of this particle by adding a extra momentum to its linear momentum. So what I want to say is, so let us see in short what will happen. So B will affect the momentum through its vector potential A, and this will introduce a non-zero phase difference or relative phase difference between the counter propagating wave. So that means there won't be no constructive interference between the time reverse path. So this is the qualitative explanation. To calculate the phase accurately, so we need to see what is the change in momentum or change in wave vector because of this field. Then from that, if we integrate the wave vector over a line integral, so we can calculate what will be the relative phase shift. Okay, so there won't be any constructive interference. That means there won't be any weak localization. It won't be there. So let us see how the weak localization can be lifted. So we are interested in what is the phase that the particle will acquire whenever it returns back to the same point. Let's say this is some area S and the particle is returning to the point 1 or to a point 2, which is at a distance which is much less than the uh, inelastic scattering length. So for this, because if you recall, B is his call of fate, and the vector potential, it will change the momentum. So initially we have MB, now we have a extra potential due to the extra momentum because of this vector potential. And for electron, you can write it as minus E. So that means the change in wave vector 1 by h cut MB minus E. So this is in the presence of the vector potential or in the presence of magnetic field. So here you can clearly see the phase as well as the wave vector, they depend on the vector potential. So that means if you want to calculate the phase from point 1 to 1 or 1 to a point 2, which is where the distance is much less. So this will be 1 to 2 KDL. K is 1 by h squared, 1 to 2. Or I can write it as, let me write the final expression because it's already there in the lecture. So you will get 1 to 2 VF dl minus 2 pi E by H ADL from 1 to 2. In the second term here, from 1 to 2 means you are traveling through a closed loop. So this is nothing but the integration over a closed loop. And from the Stokes law of electrodynamics, so there is a theorem in electrodynamics. So whenever you have a line integral of a vector potential over a closed loop, so you can write it as surface integral of curl of this vector potential over this over the surface that is enclosing the line integral. So that means over this surface. So these are the fundamental relation that we need to remember also, because it will be helpful while solving few problems. So curl of A, it is BDS, and summation integration of BDS. If we recall, this is nothing but the magnetic flux. So similar to electric flux, we have magnetic flux. We can write it as this is phi m or phi. So the phase change in the presence of a magnetic field. Now we have a KFL minus 2 pi E by H E phi. This is the phase change in the absence of the magnetic field, and this is the phase change in the presence of the magnetic field. So, and if we recall, the weak localization, it will occur whenever this clockwise path, it will interact with the anti-clockwise path, let's say this one, and they interfere constructively. So for the reverse path, which is the time reverse path, we can write delta phi 2 to 1. So KFL, this is the geometric phase. This will remain same, but this sign will change. Now this will be plus 2 pi E phi by H, because the now the dl is reversed, but the vector potential, it is always in the same direction, which is defined by the field. So because of a change in sign of A and dl, we'll see a sign change for the reverse path. So that means the total, if this clockwise and the anti-clockwise path will, but the phase difference between them in the presence of a magnetic field will be delta phi. This will be delta del phi 1 to 2 plus del phi 2 to 1. So phase difference, so this will be minus. So we have 4 pi E by H pi. Or we can write it as 4 pi by pi 0. Pi 0 is the quantum of magnetic flux. So that means there is a relative phase. So in the presence of a magnetic field, there is a relative phase difference between this time reverse path. So in the previous where we have seen constructive interference, now they will interfere. They are out of phase. So it's possible to see that they won't interact, and the weak localization can be lifted in the presence of the magnetic field. So this is how we can, this is the quantitative relation of what is the phase difference of this time reverse path in the presence of the vector potential. And for one path, for only one path, it is half of this value. Okay. So now let us see what is the phase breaking length. Phase breaking length, or this is also we call it as phase coherence length, L5. So L5 qualitatively it is the length scale over which the electrons, the phase of this electron will remain conserved during the transpose. So the phase won't change if we have a path which has a length scale of L5. So L5, we can write it as this is the longest trajectory that can contribute to weak localization. Because if you recall, weak localization, it depends on the phase coherence. So let's say we have a system where the length, the path length traveled by this, um, uh, sorry, time reverse path, this is greater than the L5. So that means there won't be any weak localization because the phase will, there is no phase coherence between them. So they will interfere destructively with each other. So that is why to see the weak localization, the length should be less than or equal to L5. And if you want to break it, then the length should be greater than L5. So what I mean is that uh, this is the longest trajectory that will contribute to the weak localization. And if we assume that the path is L5, it's like a circle. So the largest phase shift between this time reverse path that can lead to weak localization, you can write it as this will be corresponding to the largest area, which is SL5, and this is pi r square, and r is L5 by 2 pi square. Okay, so this is the largest phase shift that we can see to that the system can have for the weak localization, or so it is like a transition point between seeing the weak localization and not seeing the weak localization. Okay, so that means it will also set a limit on the magnetic field. So there will be uh, there will be a critical field over which we can see the localization and below which we can't see the local. So it all depend on the dot product of B with S. So if the area is less, then we need to have high magnetic field. But let's say we don't have a system where uh, experimental setup where we have high magnetic field. So for that we need the longest trajectory where L5 should be less than, sorry, the length should be less than L5. So it's like a trade-off between magnetic field and the area of the trajectory. Okay. So that means we have a critical magnetic field. And this critical magnetic field, that means this is the minimum field that is required. So minimum, what will be the minimum phase difference between this time reverse path to have destructive interference? So we don't want to see the weak localization. So that means they should interfere destructively, right? So the minimum phase difference between them should be pi. So it should have pi phase difference so that they can interfere destructively, and we can calculate what is the B field corresponding to this uh, phase difference of pi. So that means the phase difference, and we have seen also the phase difference between this time reverse path is 4 pi, pi by pi 0, or 4 pi, pi is, pi 0 is h by e, and pi is b dot s. So we want to calculate the critical field corresponding to this largest phase shift. And we have seen the minimum phase difference is pi. So if you put it, so this pi will cancel. And if you put this SL max here, so you can calculate it by yourself. So you will find that the critical field, it will be given by the L phi square is pi 0 pi by L phi square. So sorry, with this. So critical field, you can approximately write it as phi 0 by L phi square. Okay, so this is the minimum magnetic field that is required to break the weak localization in a area which is given by this phase breaking length. Okay, so in the next part, we have seen. Okay, so there is an effect of temperature on the weak localization also. So if you increase the temperature, the inelastic scattering will increase. So phase coherence will decrease. So that means the weak localization will also decrease. So this is one of the, what will be the effect of temperature on weak localization. So when temperature increases, inelastic scattering this will increase. So that means the page will randomize and weak localization will decrease. So this is the effect on temperature. And also effect of B field is as B will increase. So that means the relative phase between clockwise and anti-clockwise state will increase. So that means weak localization will decrease. So this is some of the qualitative explanation on what will happen when we increase the temperature, as well as what will happen when we increase the uh, magnetic field. So similar to the weak localization, we have a counterpart of this weak localization, which is weak anti-localization. So this is typically found in material with strong spin orbit coupling. So when there is a strong spin orbit coupling, so this time reverse path, the clockwise and the anti-clockwise path, they will be coupled in different directions. So because of this, there will always be a destructive interference. So that means this is the opposite of what we have seen in weak localization. So instead of a decrease in conductivity, the conductivity will increase if we consider a material where the spin orbit coupling is maximum, or there is a significant spin orbit coupling happening there. Okay, so this is weak localization. Now we have in the next part we have seen what is the physical significance of a vector potential. Okay, so let us see in brief what is the physical significance of vector potential. If you recall the Maxwell's equation, so how did you get B equal to curl of A? So this is derived from Maxwell's second equation, which is Gauss law of magnetostatics. So divergence of B is 0. And mathematically, we know that divergence of curl is always 0. So that is why we say we can write the magnetic field as some curl of vector potential A. Similarly, for the first Maxwell's equation, for the electrostatic case, we have divergence of E is zero. And for this case, you can recall we can write electric field as negative of gradient of some scalar potential, let's say phi. Now for this mathematical expression, if we change the vector potential, let's say we are changing the vector potential to A prime, which is A plus gradient of chi, and this scalar potential is changing by phi minus dou x by dou t. So if you change the vector potential or scalar potential, these two expression, that is the electric field and the magnetic field, they won't change. So even though we are changing the vector potential and scalar potential, nothing is happening to the magnetic field and the electric field, which is controlling the dynamics of the charge particle. So that is why in classical electrodynamics, we uh, uh, we say that we don't have any physical significance of this vector potential. We say that these are the mathematical entities, which we take to calculate what will be the magnetic field and what will be the electric field for a given configuration. So with the if so this vector potential only have mathematical, so they are only required for calculating the field. They don't have any physical significance. But in reality, when we consider the quantum mechanics, where we treat the particle as a wave function, so in quantum mechanics, there exists a physical significance. So what what is the effect of this vector potential on this particle? If you say the if we look at the quantum picture, so this in short, what we can say is that this vector potential, they will introduce a extra phase factor on the wave function of this particle. So the effect of this potential is that they introduce extra phase on the wave function. And because of the extra phase, and if you study the interference of this particle, which is getting affected by a vector potential, then we'll see that because of this extra phase factor, they will interfere and we'll see a oscillation in the conductivity and oscillation in the current. So when we measure the current, we'll see oscillation. So classically, there won't be any oscillation. The current should remain constant if it either goes any path. But in quantum mechanics, we see there is a oscillation, which is because of this phase introduced by this vector potential. So in reality, the vector potential and the scalar potential, these are not only the mathematical concept, they have physical significance. So we'll see in brief that we have seen in the lecture also. So to start with, so let us say we have a solenoid and the current is flowing in this direction. So if you recall, uh, using the Ampere's law, we have calculated, well, so these are some of the concepts from electrodynamics. So using Ampere's law, we can calculate what will be the magnetic field inside the solenoid and what is the magnetic field outside the solenoid. So, and we found that B is, for inside the solenoid, it is mu naught Ni, and for outside, it is completely zero. And from this B, we can calculate the vector potential also. So expression for vector potential, it is given by phi m 2 pi r phi cap. So it is in the azimuthal direction. It is in the phi cap direction. Okay. So for this case, So let's say a charged particle is moving in outside the solenoid. So classically, we can guess that the transport dynamics of this charged particle shouldn't change because there is no magnetic field in the outside region. So that is why the trajectory of this particle, it shouldn't get affected by presence of this solenoid. But in quantum mechanics, because of non-zero vector potential in this regime, in this outside region of this solenoid, we'll see that the wave function of this particle, it will acquire a non-zero phase when it travels through this field-free region. And this is what we call the Aharonov-Bohm effect, or in short, AV effect. And what is the consequences of this AV effect? So because of this non-zero phase, we'll see a oscillation in the current. It will be there in the presence of B field for a particle moving in a ring-shaped conductor, or where two path of this electron, let's say this path or this path. So two time reverse path or two, let's say two equal same direction path, they will interact. So when they interact, because of the phase acquired by this psi 1 or psi 2 while traveling through this uh, field-free region, they will interfere and we will see oscillation in the current depending on the phase. So this is the overall consequences of uh, having AV effect in a sample. So let us see what is the exact value of this phase that is acquired by this particle in the presence of AB effect. So if we consider a conductor, ring-shaped conductor, where the magnetic field, it is confined only in this region and it is zero outside. So B is confined and outside B is non-zero. Now we want to see we are injecting current or the charge particle is traveling. So it can take either this path and reach point here, or it can take the path this one to reach point. Let's say this is the point J2, this is the point J1, this path corresponding to L1, this is L2. So it can take either L1 and L2 to reach the point J2. Now when we measure the current at this point J2, we will notice that there will be oscillating behavior of this measure current. So similar to the case we have seen, so if you recall, we have seen that the particle's momentum, it will be changed because of the presence of vector potential. And the particle momentum is given by MB as A. So that means we can calculate the K from here. So K is 1 by h cut P plus E. So phase will be KDL. These are all vectors, so instead of writing the arrow again and again, so just assume that these are the vectors. KDL, so 1 by h cut MB plus P dot dl. So this will give a phase because of the, so this will be the non-magnetic term of phase, and there will be a magnetic term. is the magnetic term of this vector potential. In the magnetic term, so the phase shift because of this vector potential, this is del theta A. This will be 1 by E by H cut ADL. Okay. So now we have seen, we want to see what is happening at the point J2 when the electron from the L1 path and the particle from the L2 path interact at the point J2. So for L1, we have a phase. So this will acquire a phase of E by H cut L1 ADL. For L2 path, so this is for L1, for L2 path, because the now the dl is in the same direction, but the vector potential is in the opposite direction. So if you recall, where a is in the phi cap direction, so that means it is circulating, or you can say, let us qualitatively say this is like this. So and it is rotating like in the phi cap direction. So if we say the L1 path, A and DL are in the same direction, but in the L2 path, L2 and the A is in the opposite direction. So that is why for the L2 part, we have the phase E by H cut ADL. This is for path L2, which is minus of L2 minus of E by H cut ADL. And this minus of H2, you can write it as minus means we are considering this path. So if we go this way, this is minus of L2 AD. So that is why this we can write it as E by H cut minus of L2 ADL. So the total phase when the path L1 and L2 interact at J2, so total phase we can write it as del theta A. It is summation of this A by H cut L1 ATL plus E by H cut minus L2 AD. And minus L2 means we are taking a closed loop. So that is why this expression you can write it as closed integral of ADL over L1 and L2. And this, as we have seen before also, we can write it as surface integral of curl of ADS, which is BDS. So this means when the path, this path and this path, when they interact at J2, so the phase difference between them is 2 pi phi by phi 0. Okay, so because of this vector potential, we'll see a relative phase difference between the path here and if the charge particle is moving from here to here. So that means if we now measure the current at the point I, because of this phase difference, it will become a oscillating behavior. So we'll see a oscillation in current, which you can write it as cos 2 pi phi by phi 0. And it is periodic in phi 0 that you can always guess. So if we have a situation like this, the period between them is phi 0. This is for the case where we assume that the particle won't backscatter when it is going from J1 to J2. So it is traveling in the same direction. Now, we can have a case where the particle will scatter back to its original point, or the point where it was started. So that means there will be a case where coherent backscattering is happening in this when the particle is going from point J1 to J2. So for that case, let us see what is the phase difference between this two in the presence of a coherent backscattering. So we are considering the same situation. We have a ring shaped conductor and the particle is going from J1 to J2. So now the particle is coming back to the same point through this. So it can go this way to come back to this point, or it can follow a time reverse path, which is opposite to the case. So this is the way the particle can come back to the point where it was started. So for this situation, we can easily case the non-magnetic phase. It will be same. So total phase is, we have seen before also, this contribute from non-magnetic term and a contribution from magnetic term. And because these are time reverse path, like the same path, but the time is reversed. So that means this will be same. And the phase of this magnetic term, they will change the sign when we take the time reverse path. Okay, so what I mean is, let's say this is A3 and this is A4, or not A3, let's say this is L3 and L4. So delta theta for L3 path, you can write it as 2 pi phi by phi 0. And for the time reverse path, L4, you can write it as this is minus of 2 pi phi by phi 0. That means total phase difference between these two paths, between the time reverse path, it is 4 pi phi by phi 0. So this indicates that there will be a coherent backscattering, and for that case, there will be a oscillation in current, and the periodicity is now phi 0 by 2. Okay, this is the magnetic AV effect, and we have seen in detail what will be the phase difference between the time reverse path in the presence of AV effect. Similar to the magnetic AV effect, we have electric AV effect also, where we study the transport of charge carrier in a magnetic field free region, and because of a electrostatic potential, so we'll see a relative phase between the time reverse path in case of electric AV effect. So magnetic AV effect, if you recall the lecture, this has been experimentally verified through carbon nanotube, or in quantum Hall effect, or in gallium arsenide uh, two-dimensional gas, or silicon MOSFET. But it is the theory electrical AV effect. It was just uh, it was proposed theoretically, but there is much less experimental validation of this electric effect. But it's theoretically it is possible, but because that uh, moving a charge carrier in a electric field free region, it is quite difficult. So that is why it was quite impossible to see it So there is no and there is few experimental validation to this effect. So for this electric wave effect, we have Q by H cut. You can write the phase that is acquired is Q by H cut VDT. And after that, we have also seen some of the experimental validation of magnetic wave effect in carbon nanotube and other some. Now we have almost covered what the concept that has been taught in week 5. Now we'll start solving the problems related to this concept, as well as first let us start from the concept of week 4. I think from this point, from question number 15. So I have suggested you to calculate it first. Let me know whether you are able to solve this problem. Let me know the answer. If not, I will try to solve. Let me go through the question again. So you measured the Subnikov oscillation and you found that the successive minima is occurring at 1 by b is 0.5 Tesla and 1 by b is 0.56 Tesla inverse. So assuming spin degenerate Landau label in a single 2D subband, what is the value of seat density Ns for this 2D metric? Okay, so let me start solving this question. So if you recall the graph between the resistivity and the magnetic field, so we have a plot like this. So in the low field region, it is quite linear, but when we apply the magnetic field, we see Landau levels. Then there is an increment, then there is Landau levels, and the steps repeats. So this is the qualitative picture of what we've seen before. Rho x6, sorry, this is for rho xy. And for rho xs, we have longitudinal resistivity. It was constant in the low field, then it starts oscillating. And whenever the Landau level crosses the Fermi energy, we see oscillation, and whenever it is in the plateau region, rho xs is 0. Now when the Landau levels move, again so oscillation, the plateau region it is 0, then again oscillation. This is rho. The red curve is for the longitudinal resistivity. And if you recall, whenever we increase the magnetic field, so when we move from lower to higher magnetic field, the filling factor will decrease. That means the number of Landau level occupied will decrease. So that means, let's say this will be nu1, this will be nu2, this will be nu3, and so on. These plateau levels, these are nu1, nu2, nu3, and nu4. In the given question, if you see, you measure the STS oscillation and find the successive minima occur at 1 by b is this and 1 by b is this. So distance between successive minima, if you see the graph, this is the successive minima. if you consider any two Landau level, this is the successive minima between the SDS oscillation. And if you see the filling factor for this successive minima, they changes by a factor of 1 for these two successive minima. So that means you can write as let nu3 minus nu2, it is 1. And if we recall the filling factor expression, it is given by the ratio of ns and the number of occupied Landau level per unit area. And instead, in the case of spin degenerate, we have 2E P1 by H. For the nu2, this is, or let's say this is nu3. 2E B2 by H. This should be 1. We just need to rearrange it and put the value of the parameters which is given in the question. One is H by 2E, 1 by B1 minus 1 by B2. Or sorry for the notation, it is nu3 U2. This is 1. And we want to find out what is the seat density. So we want to find out Ns. So Ns is 2E by H, 1 by B1 minus 1 by B2. 1 by B1, B2 is given, sorry, B3, B2 is given, and we know the value of E and H. So just put the values. E is 1.6 into 10 to the power minus 19. H is 6.63 into minus 34 by 1 by B3 is 0.56, 1 is 0.5. So this will come around 8 into 10 to the power 15 per meter square. So your answer will be option D. Okay. So is this problem clear to you? Is the steps are clear to you? Let me know if you have any doubt. Okay. Otherwise, let's move to our next problem. Okay. In the second question, we have for a 2D electron gas with carrier density, Ns is 3 into 10 to the power 15 per meter square. What magnetic field is required to reach filling factor nu equal to 3? Can you please calculate and let me know the answer, because I think it's quite easy. It is also given that the spin degeneracy is limited. That means there is no factor of 2 in the Landau level calculation. Just recall what is the expression for the filling factor, and from filling factor, just see what are the parameters that is given to you, and what is the condition, which is the spin degeneracy is lifted, what is the condition given to you. From that, just calculate what is the magnetic field that will be required to get filling factor of nu equal to 3. Nu equal to 3 means 3 Landau levels will be occupied. Okay, let me go through the steps. Nu is, you can recall, nu is given by ns by when the spin digenous is lifted, you can write it as eb by h. And this is given b. That means b is ns is given, it is 3 into 10 to the power 15. So this will give a value 4.14 Tesla. Option C. So question number E is nothing but the charge of this electron. So you can take it as 1.6 into 10 to the minus 19. Okay. So let us move to our next problem. It's given if the magnetic length LB becomes comparable to the disorder correlation length in a sample, what qualitative effect might this have on the visibility of quantum Hall plateaus? Whether the plateaus will disappear completely because LP can no longer be defined, or option B, plateaus become sharper because wave function average over more disorder, or plateaus may smear out because LL states are more strongly affected by disorder, or option D, plateaus may broaden and become more robust to small change in B. Yes, you are correct. Option B is the right answer. Okay. Question number 18. In the classical Hall resistance Rxy before quantization sets in, what is the behavior of this classical Hall resistance as a function of magnetic field? Rxi is inversely proportional to B, or Rxy is directly proportional to B square. Rxy is directly proportional to B, or it is independent of B. So before the quantization, what is the how the Rxy vary as a function of B? So quantization, if you recall, it happens whenever we break the time reversal symmetry. So when we apply magnetic field, so quantization will take place because of formation of Landau labels and all. But if you don't have any magnetic field, then what is the behavior of Rxy? Option D. No, it's not independent of B. So if you recall the lecture, so before if you don't consider the effect of magnetic field, so we are considering a classical effect. So by equating the I think I'm doing it correctly. So if you recall this equation, so we have a force due to electric field, also a force due to the magnetic field. And this we can equate it to the change in linear momentum, which is mdv by dt. So by putting the values of, and we have roughly rearranged the term. So we have put is, let's say, ex, ey, az, and b is in the z direction, 0, 0, bz, and vd is bx, vy, vz. So by putting all this term and we have rearranged it to C expression is rho j, where rho is a, now it's a matrix. And the expression of this rho matrix, so I don't have space here, let me write it here. So rho, rho xx, rho xy, this, if we recall, this is the normal resistivity, m by n square tau. And this is, if we recall, it is given by, I think, ne by b. This one is minus of ne by b. So this is without considering the quantum Hall effect. So that means there is, there is no breaking of time reversal symmetry. Because of this effect, we see that there is a non-diagonal term, and this we call is as classical Hall resistivity. And for resistance, it is inverse of, I correct. Okay. Is it NE by B or P? I think it is P by NE. Sorry for the wrong. Okay, so this is B by NE. So that means resistance is directly proportional to B. So if you don't consider the quantization, resistance is proportional to B. Okay, option B. Question number 19. S channels in a quantum Hall bar are 1D chiral conducting modes at the sample boundary, or these are bulk diffusive states spanning across the entire sample. Option C, localized impurity states in the bulk. Option D, conventional metallic surface states unrelated to magnetic field. So what is the definition of A states in a quantum Hall bar? What do you think? Question is given H channels in a quantum Hall bar. So if you recall, these are unidirectional 1D. Chiral means unidirectional. 1D chiral conductive modes at the sample. Bulk diffusive state spanning across the entire sample. This is not the A state. This corresponds to the bulk mode, which leads to SDS oscillation. Okay. So the ACE channels, these are, recall, these are the states at the boundaries. And these are unidirectional. Option A. Okay. Question number 20. It's given in the integer quantum Hall regime at a filling factor nu equal to 3. The Fermi level at low temperature lies deep inside the n equal to 2 Landau level, or option B, exactly at the center of n equal to 2 Landau level, or it lies between n equal to 2, n equal to 3 Landau level, or option D, it lies between n equal to 1 and n equal to 2 Landau level. So it's given nu is 3. Now you need to locate the position of Fermi level. with respect to the quantum number n. Okay. So if you recall nu equal to 3, that means 3 Landau labels, they are completely filled. So that means if they are completely filled, there won't be any STS oscillation. So they lie in the plateau region. So that means they lie between two quantum states. Now to find out what is the quantum states. So if we recall, we write the energy of this Landau orbit as En is n plus half h cut omega c. Omega c is the cyclotron sequence. So, and n can start from 0, 1, 2, 3. So for harmonic oscillator, n start from 0. So it's given 3 Landau levels are occupied. So the levels will start from the lowest level, right? So it will start filling from n equal to 0, then n equal to 1, then n equal to 2. So that means all these Landau levels n equal to 0, n equal to 1, n equal to 2, because nu is 3. So that means 0, n equal to 0, n equal to 1, and n equal to 2 will be occupied, but n equal to 3 will be empty. So that means the Landau level, sorry, the Fermi level, which lies in the plateau region, it will lie between n equal to 2 and n equal to 3. This is how you can interpret what is the position of Landau. Options B. So is it clear to you? Let me know if it is not. I will try to clarify it further. Okay. So in the question, it's given that nu is 3. So from the lecture, if we recall, this means 3 Landau levels are fully occupied. These are occupied. That means Fermi level will now decided here, right? This is the position of Fermi level. But we don't know the position of Fermi level with respect to the quantum number. Because in the question it is given in terms of quantum number n. So that is why, if you recall the lecture, for this cyclotron oscillation in the presence of magnetic field, we have quantized the energy as the energy of harmonic oscillator. So we have taken En is n plus half h cut omega c. And the energy of first level will be half h cut omega c for n equal to 0. Second level is, you can calculate it by putting 1 for n equal to 1. Third is 2 plus half h cut omega c. And because three energy levels are occupied, so that means n equal to 0, n equal to 1, n equal to 2. These are already occupied for nu equal to 3, and n equal to 3 is not occupied, which is the next higher state, n equal to 3. So that is why the position of the Fermi level will be between n equal to 3 to n equal to 2. Okay. For the next question, we have, if the state density Ns in a 2D electron gas is increased by applying more positive gate voltage while keeping B fixed, how do the position of integer quantum Hall plateaus in B change? So if you increase Ns by increasing the gate voltage, but you are not increasing the magnetic field, so this is fixed. Then what is the effect on this graph? How the plateaus will change? Whether they will shift to higher V values, or higher B value means this plateau will slip to here, this plateau will shift here. Option B, they shift to lower V value. Option C, they remain at the same V value. Option D, they disappear entirely. A or C? Yes, your guess is correct. Answer is option A. So the way to visualize it, so when you increase Ns by increasing the gate voltage but keeping B fixed. So that means if you recall, nu is given by Ns by 2 B E by H. So you are keeping B constant, but you are increasing Ns. So that means you are increasing the filling factor, right? So you are increasing the filling factor means you are increasing the Landau level. So nu will increase and more Landau levels are occupied. That means more A states will appear across the sample boundary. This means all conductance will increase. Or I think we can guess it. So if we recall the graph, this is for nu 1, nu 2, nu 3, and the conductance related to this is given by nu V square by H. So that means the plateaus will move to lower V value, not the higher V value. So that means option B is the correct answer. Option B. You can guess it from here. Ns is increasing means nu factor is increasing. So nu factor is increasing means the plateaus will move to the lower magnetic field part because it is more and more Landau levels are. Okay. So this is all. Okay, I have one more. Okay, this is conceptual one, and this we have seen before also. In Subnikov-Diaz oscillation measurement, oscillation in longitudinal resistivity are periodic in 1 by B. If successive minima occur at 1 by B1 and 1 by B2, what does the spacing, which is delta 1 by B, primarily tell you? Whether it tells about the mobility of the sample or the 2D carrier density or the temperature of the lattice or the effective mass of electron. This you can recall, we have seen one numerical problem for this. So this successive minima will help us to calculate what is the 2D carrier density Ns. So answer is option B. Ns is given by 2E by H delta 1 by B. Okay, so this is all about week 4. Now let us start the problems for week 5. We'll start from easier question, easier conceptual, then we'll move to numerical problems. So the first question is, which of these following best describe how the phase change due to the magnetic field depends on the enclosed area of a diffusive loop in weak localization. So it basically asks about in the presence of weak localization, what is the behavior of phase change in the as a function of enclosed area. Option A, the phase change is quantized and can only take integer multiples of 2 pi. Option B is phase change is independent of loop area, depends only on number of scattering events. Option C, phase change is inversely proportional to loop area, thus less affected. Option D, phase change is proportional to the enclosed magnetic flux. So larger loops lead to larger phase shift. So if you have weak localization, then the phase change, how it depends on the area enclosed. Which one of this following you think is the correct option? No, the correct answer is option D. So if you recall the weak localization, this happens because of coherent backscattering between time reverse path, right? These are the time reverse path. They interfere constructively, so that is why um, we see weak localization. And the phase difference between this time reverse path or let's say one path, or also if you take for time reverse path, phase difference is 4 pi by pi 0. And pi is nothing but b dot s. This is the enclosed area. So phase does depend on the enclosed area and it's proportional to enclosed magnetic flux. Larger loops leads to larger phase. Question number 2. Weak localization in a quantum correction that increases the conductivity or it decreases the conductivity, which leads to positive correction to resistivity, or it has no effect on conductivity, or weak localization only appears in ballistic transport. Which of this option is related to weak localization effect? Recall weak localization is because of coherent backscattering because between the time reverse path. So this time reverse path, they interfere constructively. So that means what will happen to the conductivity, whether it will decrease or whether it will increase or it doesn't have any effect on conductivity. Option D is not the option because ballistic transport, there is no scattering. So there is no option of core and back scattering in ballistic transport. So that means this is wrong. So the correct option is either option A, B, or C. So if you recall, weak localization, it is because of the constructive interference. Interference between the time reverse path. So that means if there is a constructive interference between this time reverse path, so that means the probability that the particle will return to the initial state will increase. So this is what we call the weak localization because there is a increased probability of the particle to return to the initial state. And this happens because of the constructive interference between the time reverse path. So because the electron or the particle is getting diverted from this path and it is coming to its original path. So that means the conductivity will now decrease. So this will decrease the conductivity and we will see a positive correction to the resistivity. So option B. In case of weak anti-localization, there is a destructive interference between the time reverse path because of the spin orbit coupling. For that case, we'll see a increase in conductivity. Okay. So for this question, answer will be option B. Okay. Question number 3. In the lecture, the return probability for a given path from 0 to 0 is calculated as Ti 0 to 0 is 4 Ti square. This we have seen in the lecture. That is the return probability is 4 times of square of Ti square. The factor 4 arises because there are two independent paths with random phase. Or option B, magnetic field doubles the probability. Option C, only the diagonal terms survive in diffusive transport. Option D, the time reverse pair has identical amplitude and zero relative phase. So the interference term is plus 2 Ti square. So why does this 4, what is the reason behind this factor 4 in this return probability? What do you think? Okay. So if you recall, return probability from 0 to 0, this we have seen in the first part of our lab session. You can write it as Ti plus square plus Ti minus square plus 2 Ti plus Ti minus cos pi I plus minus pi I minus. And the return probability, so the particle to return to its original state. So it can return by a clockwise path or it can return by a anti-clockwise path. So these are the time reverse path. And because these are the time reverse path, so what we mean by time reverse path is this is the same path, only the direction at which we are moving is reversed or only the we are reversed in time. So initially we are going this manner. In the second case, we are going this manner. So these are the time reverse paths. So in a sample, we can have either clockwise state where by which it can returns to this initial state, or it can have an anti-clockwise state where it can return to its initial state. And for clockwise, we have written this is Ti plus, and for this, the wave function is Ti minus. And for every time reverse path, the amplitude, the probability will be same. So that is why Ti plus is Ti minus. And because this is the same path, the phase accumulated will be same. So this we are considering without any magnetic field. Okay. So that is why the phase factor, they are same whenever if you go either clockwise or if you go anti-clockwise. So because of these two condition, if you put in this return probability, this is same. So this will give 2Ti plus square. And this is the interference term. So this is same. So that this is cos 0. It will give 1. So the interference term is now 2Ti plus square. So that means the factor 4 arises because the time reverse pair has identical amplitude and zero relative phase. Option D. So what happens when we apply magnetic field? Okay. So if you recall, initially we have a phase because of this geometrical path, right? This geometrical path will give a phase, and this also give a phase because of this uh, geometry of this path, and without the magnetic field we say that these are same. Now when we have magnetic field, so that means if we recall, the momentum will now change. So there is a extra momentum factor because of this magnetic field which acts by vector potential A. So from this, if you calculate, we can calculate what will be the wave vector. This is 1 by h cut mb minus E r, and the phase for one path. So we are considering one path. The phase for one path will be, let's say this is del phi Ti plus. This is the phase accumulated. This will be KDL through the Ti plus path. So we know this. This is 1 by h cut mb minus 1 by h cut A dl. This is the non-magnetic term, which is the geometric phase, which remains same whether you go clockwise or anti-clockwise. And this is the magnetic term. So this magnetic term, this will change the sign whenever we consider the reverse path. Because if we recall, A is in the phi cap direction. Okay. So to clarify it conceptually, so let's say A is in this direction. So for one path where we are moving in the same direction of A, ADL will be, the sign of ADL will be, the dot product will give positive value. But if we are moving in the anti-clockwise path, so for this path, A and DL, they are in opposite direction. That is why the dot product of ADL will give a minus value. So that is why this magnetic term will now change. Okay. So that means delta theta Ti minus is the non-magnetic term, which is same as before. And there is a change in sign. Initially it was minus. Now this is plus. This is A by h cut ADL. So now if you take the phase difference between this time reverse path, so delta theta is delta Ti plus minus delta theta. Or we can take, otherwise taking the maximum value, then the minimum. So the non-magnetic term will cancel, which was cancelling earlier also. Okay, it was cancelling earlier, we got cos 0. Now it is, this is also cancelling, only these two magnetic term, they will add up. So instead of zero relative phase, now we have a non-zero phase because of this clockwise and because of this vector potential. And we write it as ADL. And if we recall, we have calculate, it was coming around, if I'm not wrong, this is 4 pi by pi 0. So depending on the phase, now the probability of the return probability will now change. Okay. So it's possible to have a destructive interference or a constructive interference depending on the flux enclosed. Initially phase was same. Now there is a factor of, there is a relative phase between the time reverse path in the presence of magnetic field. So I hope this is clear. Let me know whether you have any other doubt. So whenever you have magnetic field, always start from here. Okay, the linear momentum will now change. Depending on the linear momentum, K vector will change, which is the wave vector, and the phase depends on the K, so phase will now change. And for the time reverse path, this sign, the magnetic sign of this magnetic term, it will change. Okay, question number 4. Consider a closed diffusive loop of area A in a perpendicular magnetic field B. What is the phase difference between a loop and its time reverse partner due to the field? This we have seen in question number 3 also. What is delta phi for this time reverse path, which we have written as 4 pi by pi 0. 4 pi is nothing but the magnetic flux P dot A, and phi 0 is h by A. This you can rewrite as 2e BA by h cut. So the phase change between the time reverse partner, it is 2e BA by h cut, and this grows linearly with magnetic field and the enclosed area. Answer will be option A. Okay. Question number 5. In a disordered 2D metal at low temperature and zero magnetic field, what is the most direct physical origin of weak localization correction to the root conductivity? We see that in presence of weak localization, sigma, there is a correction to the sigma, and this is given by the weak localization. So option A, increased electron photon scattering rate at low temperature. Option B, opening of an energy gap at Fermi level due to Bragg reflection. Option C, screening of impurity potential by mobile carriers. Or option C, enhanced backscattering due to constructive interference of time reverse diffusive paths. So why do we need a correction to the conductivity in the presence of weak localization? Which one is the correct option? Okay, so correct option is option D. So why do we need a correction to the sigma in the presence of weak localization or in the presence of zero magnetic field? It is because of there is a coherent backscattering and there is a constructive interference between the time reverse path in the absence of magnetic field. Okay, so weak localization, always remember this happens because of weak localization means the light or the particle is getting localized. Okay, so localized means it is returning back to its original position. So this is what we call the coherent backscattering. And why there is a localization? Because there is an increase in probability. And increase in probability will happen if there is a constructive interference. If there is a destructive interference, there won't be any localization. If there is a constructive there, then there is a constructive interference. So that is why the particle will return to its initial state in the absence of magnetic field. It is because of the constructive interference between the time reverse path. So because the time reverse path interfere constructively, so that means there is a non-zero probability that it will return. And if you recall, we have calculated the non-zero probability is 4 times ti square for one path. Okay, so option D. So the concept may seem quite confusing when you go through the uh, because there are many concepts that has been covered in week 5. There is weak localization, there is anti-localization, that is AV effect. So please go through the lectures in detail and try to understand it. Try to write it down what is happening here, what is happening here. So only the if you write it down and clear the concept in your mind, then only at that time you will be able to solve the problem. So I will suggest go through the lectures or go through the first part of this live session to understand the concept better. Okay. Okay, I think let us start. Let us solve question number 6. Then we'll see the remaining problem in the next session. Okay. Other than that, if you have any other doubt, please let me know because we are short in time now. Only 3 minutes left. So I will try to clarify your doubt first. Okay. So let's see question number 6 quickly. Question number 6. How does a weak perpendicular magnetic field modify the interference responsible for weak localization in a 2D field? So there is weak localization that is happening in a sample because of the constructive interference of the time reverse path. Now we apply magnetic field to it. And we have seen magnetic field will add extra phase factor, which is 4 pi by pi 0 for the time reverse path. And this will, okay, let us see the option first. Option A is it doubles the degeneracy of electronic states at the Fermi level, enhancing the localization, which is not correct. This is not correct. And option B, it only changes the spin degeneracy, has no effect on orbital phases, which is also not correct. It does changes the phases. Option C, it adds a random scalar potential that completely localizes electrons in real space. This is not the option. Option D, it introduces a no bomb phase between the time reverse loop, suppressing their constructive interference. So the correct answer is option D. Because whenever you have a weak localization in a sample and if you put the sample in a magnetic field, which is greater than the critical field, then there will be a phase factor. There will be a relative phase factor between the clockwise and anti-clockwise path, which we call the time reverse path. Because of this phase difference, now there is a possibility that we can leap the uh, mm, what we call weak localization, because there will be a destructive interference between this clockwise and anti-clockwise path. So that means in if we want to suppress the weak localization, we can apply the magnetic field, which will introduce a phase factor, and this will make the clockwise and anti-clockwise state in out of phase. Option D. Okay, we'll stop from here. Let me know if you have any doubt before stopping. NPTEL team to share the previous NPTEL assignment. Okay, I can say, but I don't think they will share it because uh, okay, I will suggest you if don't worry about the previous NPTEL assignment. So try to solve the problems of this assignment, because I have compared the questions and the questions are quite same. It's not like they have asked different question in the previous part. They are quite same. The concepts are quite same in both the assignment. So even if they say, then it won't be any help. Okay. So only thing that I would suggest is go through the lecture contents and try to understand the concept better and better. Okay, so don't worry about the exam, because exam will be mostly, it will be the concept or the pattern will be mostly what you have seen in the NPTEL assignment that has been floated now. Only thing that you need to go through is the lecture contents, as well as don't just recall, don't try to remember the, just go through these statements like in a vague manner. So try to understand it deeper. What will happen? Like try to question yourself. Like what will happen if I have a magnetic field to the weak localization? So try to question your whenever you are trying to read, try to write down whatever has been covered in the course. Try to question yourself, your concept, whether you have uh, clarified the concept in better manner or not. And if you have any doubt while going through the concept, you can ask me in the live session. I will be happy to solve your doubts and clarify your doubts in better. Okay. So don't worry about the exam. Just go through the lecture content and the slides and try to understand the concept, and go through the live session also, because I try to cover whatever covered in the week, the concept as well as the numerical problems in the first part. So that's why I try to keep the first part of this live session as a conceptual part. Then I try to solve the problems, because it will be helpful to you to revise the concept and get clarified. Okay. So go through the live session, go through the problems. It will be enough for you to get a good score in the exam. Okay. Any other doubt you have? If not, okay. So thank you for joining the session. I hope this is helpful to you to solve the assignment problem. Let us meet on next Friday, same time from 6 to 8, to solve few more problems for week 5 and to see what is the concept that has been covered in week 6. Okay. So I think we are typing something. Let me know if you have doubt. Okay. Okay, so thank you for joining. So for now, let us stop the session. Bye, everyone.